All right, we're live. February 25th. I am getting later and later in doing this. It's just because the day is just so busy with other stuff. I don't really have time. However, that said, doing LeetCode is something I have to do every day. This is something I made a promise, and I will not give up, even if I'm really tired. Anyway, let's take a look. Actually, sometimes I feel like LeetCode is sort of how should I put it? A little bit, change of mind. It's good. It's always good to have a little bit change of mind whenever you get stuck somewhere else. And I consider this as type of entertainment for my brain. All right, let's take a look. Hopefully, it's not too hard because it's really late right now. I usually cannot think very well when it gets late. All right, let's see. Shortest unsorted continuous subarray. Huh. All right. Given an array, we find one continuous subarray that if you only sort the subarray in ascending order, then the whole array will be sorted in ascending order. Ah, okay. I get it. So we're gonna do what? 5. It's like that's right. This one has to be sorted. 10 to the 4th. Yeah, it's ON. Jeez. So they probably will allow ON squared. 10 to the 4th, I think, yeah, they allow ON squared. So we have a little bit of leeway here. Well, let's take a look. The continuous subarray, all right? I have to sort it in order to make it a ascending order. So, what we can do? What can we do? Oh, a lot of things going on in my mind right now. Trying to think what would be the best. Basically, what we're saying is, I mean, the whole length, right? Definitely is sorted. Well, we can sort the entire thing, and then just compare. See uh, where things do not match, right? So we can sort it, and then just compare one by one. Once you have a mismatch, that is your starting point. And then keep going, keep going, keep going. So your starting point, you find, and you need to also find the end point, which means you go from the start and go from the end. Oh, right, yeah. And log in. And log in. I think nlogin can solve this. Yeah, I know. It does ask us for a ON solution, but for this type of question, especially if you really want to be very pragmatic about it, you say, okay, I only want to solve this for interview purpose. Then this is how you do it for interview purpose. At least pass the first question in the interview. If this happens in the interview, I can definitely see this happen in the interview. If this does happen, then what should I say? Then you'll probably do this for the first option. You do it, and then once you solve it, they probably will ask you for the ON solution as well. And I just realized this is probably not the best way. Is this the best way? Oh, what are you doing? Ah, come on. Yeah, I cannot talk and do this at the same time. Talk. I can't do it. All right, so what we're gonna do is, can we zip it? I'd rather not. You know what? Let's just do this. For left in range 0 to len nums, right? If nums left is not equal to sorted nums left, then we're gonna break. do the same thing for the right. So instead of left, we are going to do right. And we have to change this. So let's do this, -1, -1. And the first one, okay, and then we're going to return right minus left. Hold on, it's a number, right? Total number. 0, 1, 2, 3, 4, 5. 5 minus 1 plus 1. So I have the plus 1. Okay, let's run some test cases. Let's hope this one's correct. And if it's correct, we can use this as a, what should I call it? Use this as a, oh, I already see an error coming in. The second test case. It's going to be a very weird number. Yeah, we'll see. We'll see how it goes. But I'm pretty sure because the right and left, the left is going to be bigger than right. So this is not going to be right, but I want to just finish this. Let's just get this done, and then see. Oh, we have a list out of. Oh, -1. Reference before. Oh yeah, that's true. Okay. Let's do. There are a lot of issues. If you think about it, there are a lot of issues. So what we can do is I have to set up left and right, 0 and nums -1, and let's just instead of do here, we do I, and then once it's not, we say left equals I. Here, let's just do J, and then once it's not, we're gonna say right equals J, and then we do this, and then we'll fail some and pass some. Yeah, because I walk all the way to the end, the left and the right all the way as well. So the result, why is this positive? Oh, because I did not, oh, this one did not hit. Did not hit at all. Okay, which means if yeah, if they hit, if it's smaller, yeah, if this value is smaller than the length, that means that's the answer. If this value is equal to the length, that means the left and right did not actually move. So the original one is sorted. So it's going to be this if let's just put in a res, and then when the return res, if res is smaller than len nums, else I'm going to return 0. Yep, let's do it. I think it shall pass with not good runtime because it's on log n. Oh no, we have a wrong answer. Oops. Huh. What type of wrong answer is this? I don't want to see. Let's play around with it. Let's see if we can find. Okay, so if we run this, oh man, this is wrong. Yeah. I run it. I try not to see. I'm trying not to see. Okay, this is correct. Okay, what situation will result? Okay, we have not tested a case like this. 5, 4, 3, 2, 1. How would this one go? This one should be 5. Your answer is 0. Okay, we have a wrong test case. I still did not see. This is all on me. I was trying to figure it out myself. 5, 4, 3, 2, 1. This should be 5. Oh man, it's really hard. I'm trying to just go really fast and don't see. My answer is 0. Correct answer is 5. And we can take a look. Yeah, so what happened here? Oh, because I said I return 0, which I should not return 0. I want to do another. Okay, let's do it this way, and then we say if sorted equals nums, and return 0. And here we can just return this. Yeah, that shall pass. I also want to try a few more things. Yeah, this the runtime gets worse and worse. Okay, so this one will work. I'm just curious. What if I do 2, 3? This should still be 5. Yeah, okay, that's correct. We still haven't seen a wrong answer. What could else be? Let's try it again. Submit again. Yes. Okay, we passed this, but the runtime probably pretty bad. Sometimes I don't understand. You know, sometimes I don't understand how is this possible? This is O(n) log n, right? This is O(n) log n here. This is O(n), basically. And then this is also O. There's lots of this. It's O(n) log n for sure, but give me a very good runtime. I bet you if I run the same algorithm again, this is something I've found on LeetCode. If I run the same thing again, I'll probably end up like here, somewhere here. Anyway, so we passed this, which means this solution does work. But the problem, we have 2 issues. First, I want to see if I can avoid this. This is just like a sore in my eye. It's just terrible. Oh, I think I know how. Because look at here, all right? We have left and right we set up at the end. And once we start going, if we have not set this, right? Which means we just keep going, I increment left does not change. So left, let's make it not 0. Let's make it, some value that's not 0. Let's make them like outside, right? So if I break here and if I have not broken, which means if this is true, then left is going to be, let's just make it -1 and make this into 1, right? And I don't want to do this, so they're gonna go, and then we're gonna say if left has not moved, then it is pretty certain that, actually I can make both like -1, right? Make both like impossible, and then we just say we're gonna return 0 if left is smaller than 0. I also want to return this, and it still pass, because then we combine the 2 together, right? We check assorted nums and nums are equal. We use these 2 loops. They will help as well. We might even, we can actually, we can do it here, right? We can say, we're gonna break, so we say else for this, we're gonna break else, which means break has not, we just return 0 right here. and we can do this. Let's do pass. Because if we have not encountered any issues, that means the sorted num and the regular num is the same. So we can return 0 already, which means it's sorted, the original. Only if this is not true, right? Only if this is not true. In that case, we don't even need to specify it first. We can just do I and j, and then we just do, we don't even need this, nor do we need this. And we just do j minus I plus 1. This shall pass as well. Yes, because we're checking if it fits. If it fits everything, then we just return 0. If it doesn't fit, that means at least there are some place in the original num that need to be, that's unsorted. Then we go the other side. So yeah, this is more satisfactory to my mind, but this one will run at a slower pace. I am almost 100% sure. I think this will go, I don't know, I think this will be slower. Yeah, see? See? That's what I'm telling you. It's going to be slower. Yeah, I'm going to record this number. Okay, I'm going to say this. Yeah, this is a straightforward method. We first sort the original array to obtain the target. Then we compare the original array with the sorted version to find the first and last element that first and last element that do not match, and the position indices of these two elements determine the length of the unsorted subarray. If no such mismatch element exists, that means the original array has already been sorted. We return 0. So this is O n log n, and we run. Let's just take 192 milliseconds, because the other one's absolutely overestimated. Now we found this solution. Go back here. See if they have a solution. So we can always check, but kind of before the check, let's try if we can do it O n. So if we want to do it O n, which means we're gonna scan it, right? We're gonna scan it. So we scan, and we find, oh yeah, I think we can do it. So we scan, that's good, and this is no good. Whenever we have a drop, that means this one must be bad. And go backwards, this is good. Boom. So this is not descending, which means this must be bad. Yeah, because we have a kink, right? We have a kink here. No matter how the other one, as long as we have a kink, it's not a strictly ascending. As long as we find a descending, then the one that causes the descent, which is 6, that's the cause of descent, or 9, that's causing the problem. Not 10, it's 9. Is it 9 or is it 10? I mean, we go this way, we need to be ascending, and then this causing a descent, so we think this is bad. So from this, we want a descent, and a 10 is the first one. So 10 is an ascent. The causing of ascent is this. So yeah, we can do it in ON. I think so. I seriously think so. And it's actually not that hard to go ON. So what we do is for I in range, we're gonna go 0 to land nums. Alright, we're probably gonna do land nums a lot. Let's just set land nums somewhere else. So we're gonna do n minus 1 if nums nums I plus 1 a plus 1. If this is smaller than nums I, right, then how about the value is the same? I never tried it before. Say 6, 6. What would we have? That'd be 3, 2. That'd be 2, yeah. So yeah, so if it's smaller, then I'm gonna break. Do the same thing for the other side. So it will be for j, this will be from n minus 1 to 0 actually. So we don't want to hit 0. And I want to say this is going to be j minus 1. If j minus 1 is larger than nums j, I'm going to break. And if we do not break, that means everybody is good. So same thing, else we're going to return 0. And here we're going to return j minus 1, j minus I plus 1. I'm going to try it here. Yep, I think this one is the ON solution. It's almost exactly the same. I actually don't want to set up a new one. Let's just put len here because we only have 2 n's, so it's fine. Yeah, so make it shorter. So it's our solution 2. And this is ON. Let's see. Submit. Wrong answer. This is not working. How about let's check this? This one's working. Descending with repeats. I'm still not looking at the solution. Oh, yep. Find it. We have found it. Let's take a look. This one's supposed to be what? Expected answer is 6, but I only give 5. Expected answer is 6. I gave 5. Okay. So we are going to descend. So this one is smaller on the break. Good. And then we start from here. And j minus 1. J minus 1 larger than this, no. So we keep going. We're going here. J minus 1 is larger than j, so we break. So j is here. So we say we're going to do this, but in fact we have to include this as well. That is correct. How do we solve this? Interesting question. So we know I think we have to wrap around because it is so for this number to be in place, it must be smaller than this and bigger than this, right? I mean, we can actually create a scenario where we're going to have an issue. So let's say we have like 3, 4, right? And 1, 2. This one shall be 4, but I think we will give a very interesting. We'll probably give a 1. I'll give a 2. Yeah. This Yeah, we kind of find the problem. This should be 4, but we gave 2 because we will identify um, we'll identify 4 as the first culprit, and we'll identify 1 is the second culprit, which is not correct. Okay? Yep. All right. So to solve this, we need to wrap around. Not sure if that's the idea. So we want to know if this one, right? So we have to compare this to the tail. If this is smaller than the tail, then we have a chance, right? We have a chance. But what if it's something in the middle? Yeah, what if I something in the middle? Like, if we have something in the middle, right, like this. Like this. 1, 2, 10, 3, 4. Even your modified version of things can work. Expected answer is 3. Yeah, just to change the last 3. Okay, we accumulated a lot of test cases, which is good, but we kind of don't know how we're going to approach this. Hold. So, your idea of going, we will end with 10 being the wrong one because this is smaller than this. So the 10 is the wrong one. But going backwards, 4, 3, right? 3, in fact, 3 is the wrong one. And we're saying to change these two. But once you change these two, 10 is still out of order. It's 4. Huh. How do we solve this? I mean, we can just like go a full trip down, notify which ones are not correct. So we can say, wow, ON is not that straightforward. I like to find like this one first, right? So I have 3, I have 4, they're all right, and going to 1. And that's not correct. So we know that in that case, all right, let's think another way. So eventually we want it to be sorted, right? We want it to be sorted. If the start is smaller than the end, then it's certain that we have to do a full, right? If the start is smaller than, right, then the entire thing has to change. So it's trivial. These 3 cases are trivial. Now the hard part is, as we go along, say the start is smaller than the tail, then what do we do? Now, if the start is smaller than the tail, then we have 2 situations, 3 situations. Situation 1, the start and the tail are indeed the largest, the smallest and the largest. Then we can ignore them, and then we shrink inside, right? Which does not mean anything. We can shrink inside. Now, but we don't know, right? We don't know. As we go inside, if it's out of order with regard, so it could be out of order with regards to the front and the end, or it's not with regard to those. Because I'm just thinking about this case, right? This case. Your front is smaller than the back, so good, so we kind of moving in. We assume that these are good, so we move in. Now move in, this also satisfies, so we assume that this is also good. Now we move in, and we find out that this one is wrong. Now we find out this actually fits on this side, but it's wrong on this side. So what do? So we find something big, right? And then we need to compare the big one to the current biggest. Man, how do we do this in ON? How do we do this in ON? We go along, right? And if we find the min max, and if it's min and max, then we move it inside. But min max takes ON to find. That will be ON squared. If you use a heap, that is going to be ON log n as well, which is not what we want. Interesting. We have the trivial cases. Can we do the comparison again? All we need to do is to find a continuous subarray that has that violate what? I mean, if you're given this, how do you know it's going to be this one? Well, I know it's this one because I mean, if you look at these are not in violation. The one that violates is, no, this one violates, and this one violates, right? So as we go along, 2, 6, 4, right? So we note this down. And then 8. 8 is actually follows. 10, good. 9, 15. So it's actually 4 and 9 that's out of sync. But in order to fix 4 to 9, we can't just fix this. We have to fix the one outside. Hold on, this is getting very hairy right now. If we go down, what can we find? We can identify six, 4. We know 4 is in the wrong place. We can also say 6 is in the wrong place. can't just look at front and back. Well, front and back we can see in the case where the front is bigger than back, right? But in all the other cases, the front is smaller than back. It's hard to identify. If we have something that's big, right? If we go left to right when we're ascending, and then we encounter something small, then we know that this is likely where we have to deal with it, right? So there must be something wrong here. Let's see the arrow case. We kind of spent some time here, so let's see this arrow case. This is 1, 3, 2 to 2, right? So in our mind, we start from 1, 3, 2. So we go up and then boom, we drop down. So when we drop down, we know there is something wrong with it. And this is the first time that we drop down. Now we need to compare the number that it drops down to. If the number that drops down is larger than some value, how do we know? Like 3, 4, 1, 2, 5, right? If we do 3, 4, 1, 2, and 5, this shall be 5, but the quick scheme is not going to work. Oh no, this is 4. Ah, this is 4. Yes, this is 4. Because we only need to change these 4. If 5 is bigger than 3. If the back is bigger than the front, man, I just have a lot of cases I couldn't figure out. Hold on, let's try it again, right? We go from left to right. As we go from left to right, we're constantly increasing. And then we'll hit a moment when we decrease. Now, when we decrease at that moment, we know the current max. And we know the current mean. So we know the mean max at that point. And then we need to decide where the change needs to be. So what I'm saying is, as we go here, 3, 4, boom, 1 drops down. So we know current mean is 3, current max is 4, and then the current, and then we drop down. So the drop down, we have to compare. I'm just thinking compared to the current mean. If it's smaller, that means everything needs to change up until this point, right? And if it's bigger, like this case, 1, 2, 10, 3. 3 is bigger than the mean. Then what? Then we have to see. Then we know something is wrong. Like the ordering here is not right. Right? The ordering is not right. But this could be like, it could be bigger than this, but smaller than the second one. So let's say, what if like 1, 1, 3, like 1, 3, 10, 2, right? We drop down to 2, and we know that 2 is bigger than 1, so the drop does not affect the front, right? The drop does not affect the front. like every time we drop, we need to check the relative from here to the front. So we drop to 2, the front is fine. So the current concern, we're going to move on to here, to 3. And then we're going to compare it again, 2 and 3. Now 2 is smaller than 3, which means this is our current start, because this and this is mismatched. And then we're going to keep going. It will go up or drop, right? When we drop, we're going to compare to, so we already know, right? So here we already know this is the start. Yeah, we keep moving, right? We go up and then we drop. When we drop, we start compare with the current front. And if we are bigger than the current front, we keep walking until we find a number that is bigger than me right now. And once we find the number that's bigger than me right now, we know this whole lot needs to change. Then what? We keep going from here. We keep going and it either drops down, but it doesn't matter if I drop down because I already know from here to here. Oh no, we have to, if it drops down even more, then say this is 4 and this is 3 and we have a 2, right? We go to 3, we say, no, this is a bad example. No, it's this is going to be 3 and this is going to be 4. So 1, 3, 10, 4. So we drop down to 4, and then we can actually go backwards to find the first number that is bigger. First number, the last number that is bigger than 4. So we go back, 10 is bigger than 4, which is sure, and 3 is not bigger than 4. So currently we stay here. It's 10 and 4. Now I keep going to 2, right? So 2 is smaller than 4, which means 2 is also looking at 10. And then we need to go, because we are dropping, so when we drop, how do we know we drop? We know we're dropping, so when we're dropping, we look at here to go front. 3. 3 is larger, so now the pointer is pointing to 3. And we keep going. If we drop, now we keep moving on, but now we're not dropping, right? We are incrementing, so we increase. Now, when it's increasing, we do not care. Yeah, because what we care is the current nadir. This is the current nadir, right? So as we go along, we need to find the minimum number. Not really the minimum number. How should I say? Just like along the way, the bottom, right? We find the bottom, and once we, because it's go up or go down, right? We go up, that's what we want at the beginning, and then we go down. So when we go down, we can identify where this trend needs to be reversed. We just need to identify the value that's just big than the down. And then we keep going. Every time we keep going down, we move the pointer forward. And we climb up, we don't move. Right? We climb up, we don't move until, so we go 2 ways. Yes, I think this one will work. we run it two ways. We go left to right to find the leftmost that we need to change. And to find it, we just keep going. We record the smallest value as we're traversing. So how should I say this? So we go up, and then we go down. So when we go down, we need to compare, and we go up. We don't do anything if it goes up, because it goes up. If we try to find, it's going to be the same value. So we go up, we don't care. Go down, we compare. Go down, we compare. Go down, we compare. That's kind of identifying the left side, which one should change. And then we do the same thing on the right side. We'll write in, and then we go down. So whenever we go up, we need to look to the right to find the one that is smaller than me. And that's be the one that we need. So overall, every value at most will be visited twice. Okay, let's see if this one works. And we're gonna borrow this test case as well. 1, 3, 2, 2, 2. So this is gonna be expected 4. So we're gonna run it 2 times. So what we're gonna do is, how shall we say this? For I, that's fine. If nums I plus 1 is smaller, so we find something smaller, then we need to run a loop. And we're going to just say left equals what? Left equals minus 1. Between left equals I don't know what value should I initiate with. So when it's smaller, then we're gonna go this. This will be the first left, and the left doesn't change. We're gonna start from left. Yeah, we're gonna have to start from left. All right, it's gonna be like this. We left initialize to minus, so we're gonna do this, right? And we say if left is smaller than 0, then we do II equals I, right? II is I, because I'm doing I plus 1, right? So II equals I, and this one is currently smaller. No, I is currently bigger, right? Bigger than me. And I need to find the one. We need to go left side to find the one that is bigger than me, the smallest value that is bigger than me. So I equals 1, we're going to say while nums while II is larger or equal to 0, and nums II is larger than myself, nums I plus 1 actually. Because with I was looking at I plus 1. I plus 1 is smaller than nums I. So we set II to I, and then we're going to go left side. So if II is larger than this, and then we're going to say I minus equals 1, right? Oh, this is actually not correct. If left, this is going to say left equals this. There we go. And then there's no II, it's just left. Right, so num left is smaller, and then we're going to decrement. Actually, we already know, so this could be minus 1. And we say this is this, and then we left minus equals 1. And then until we get to 1 that left is not, then at that point, we're going to say, left, what is left? Left should be the one that is currently larger. Yeah, let's just still do I. Let's still do I. And then this, and then we minus 1, until we hit a value that is num's left is smaller, or we left becomes minus 1. And when that happens, when this all happens, we're going to go left plus equals 1. Because, yes, so that's the current left. And I'm going to keep going like this. When we increase, we don't worry, because if I increase, the left will be the same. Because I am larger than the smaller one. That's the one that really needs to change. And if it's bigger, I don't really care. And then we just keep going. And then whenever it's smaller and left is not, left has a value. And then if it's larger than, what if it's smaller? So like we keep climbing up. So every time we climb up, we don't do it. And then we go down again. That is, so how can I not change left? Can I not change left? Hold on, maybe we don't need to change left. Let's just make left as the one value in front, right? If we make left the one value in front, and then we compare, and if it's larger, then we keep doing this, and if it's smaller than nums I plus 1, that means we just, that is the, okay. And can we also solve this problem if it's like really big? Like nums I is really big, so we just climb, keep climbing, and then drop. And nums I is really, really big. And then nums left, a small value. And then we don't change. So I do think we need to make it this and do not make this change. So we're going to go all the way to the end. And left will be the first value that we do need to change. Okay, so we're going to do the exact same thing, but now we're going to change it to J, and it's going to be something like this, right? Something like this, and it's going to be the same as here. Have a right. So right is going to be len nums. I'm not sure, but I'm just setting it right there. So I'm going to say if equals, if right equals len nums, right? That means it's not correct. Now we need to make changes. We're going to say right equals. So we're trying to find the first one that's larger, right? That's larger. Then it's going to be J. So this one is larger than me. I am J. So J minus 1 is larger than me. So I want to do j plus 1, right? And then I'm going to check while right is smaller than len nums and nums right is smaller than nums j minus 1, right? J minus 1, if nums right is smaller, then we know we need to keep moving to the right. So we're going to do right plus equal to 1 until we find one that's not. But then it is possible that we'll move Alright, so the sentinel cannot be like this. The sentinel has to be some different number because it can happen that we move all the way to the front and whatever value we find, we'll check this and then we will reset the left to the wrong value, right? So it has to be like a none, right? So I say if left is none, if right is none, right? If right and left is none, then we set it. If it's not none, then we do this. And yeah, plus 1. And once we're done with both, so we go both sides, we come out, and we say, we're going to return 0 if left is none, which means it's not changed the left at all, else we're going to return right minus left. I mean, probably need to maybe land, I probably need to minus 1 because the extreme case would be the left will be minus 1, the right will be len nums, and we cannot let that happen. Run it, we pass everything. Shall we throw one more at it? 3, 4, 1, 2, 5. This one shall give us 4. Actually, we have a better idea because this one passed. We can actually run this one. But if we fail again, we're gonna run that way. All right, let's try this one. This one is, come on. Yes! We find the ON solution. It's not likely going to be faster, I think. But this is ON. This is ON. It's just ON. Yeah, it is ON. This is ON solution because we go all the way down, and the left is identified, but it just at most, each value is visited twice. So this is still ON. So this is the ON solution. This is the ON solution. We traverse the list. Traverse the list twice. Once from left to right, and identify the leftmost element that needs to be changed. Then we go from right to left and identify the rightmost element that needs to be changed. Then we're done. This is ON. However, this runtime is 204. And we hit a 68% ranking. I'm pretty sure this is ON. Although you have like two loops inside, but it should be fine. I mean, for one thing, I can probably do it here. If left is none, return 0. So we don't need to do this. Might make it faster. Try it. Let's see how long this one takes. It's the same. But it doesn't matter. We know this one is faster because we traversed once and then we already identified. All right, time to check the answer, check the solution, see if people have better ideas. Brute force. Nope. Better brute force. Nope. Using sorting. That's our solution. Using stack. Oh, when without using extra space. We did not use extra space. For ON loops, similar as what we're doing here. ON. Amazing. Looks like there are a lot of solutions. Okay, let's we have this down. We have our own ON, but we'd like to take a look at using stack. First, take a look at the code. What is this? Selective sorting. We need to determine the correct position of the minimum and the maximum element. And this we must use a stack. We traverse from the beginning as we go facing elements in ascending order. We keep pushing, okay, over the stack. This is done because such elements are in the correct sorted order. As soon as we encounter falling slope, an element which is smaller than the element on top, we know that length j isn't at its correct position. In order to determine correct position of nj, we keep on popping. Oh, this is the same, okay, this is the same technique to keeping a ascending array in a stack. So we keep pop, 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 pop until we reach the stage where the element on the top of the stack is lesser than length j. Say the popping stop at k. Now, length j has found its correct position and needs to lie at an index k plus 1. I follow the same procedure over the whole and determine the value of minimum such k. This marks the left boundary of the sorted subarray. Oh, this is exactly the same as my solution. It just I did it without using a stack. To find the right boundary, we traverse over the backwards. Yes. Then yes, this instead of popping, we just do left minus equals 1. Yep, this is the same. This is the same. So subconsciously, I was doing the stack thing. And when it's not, and then we just keep popping. Well, we have to use a little bit of ingenuity to do this, but this is 01 in space. So good, good. We know this, and we also clear the Oh, we have L. We have it left. So every time we pop, we update L. Every time we pop, we update L. And then I'm going to push I. So we're going to find the right position for this. Every time we pop, and then that's the one, that's the position that we have replaced. Yeah, and then we keep the minimum. So every time we pop, keep the minimum so we know the leftmost that we have popped. Good. And the rightmost, yes, that's good. Without using extra space. This is not using extra space. Is this the same one? Same idea? Need to determine when the correctly sorted array goes wrong. Track observing, okay, the same thing. Whenever the slope falls, we know that the unsorted array has surely started. Thus, when we determine the minimum element found to the end of the given by min, then we traverse over nums and determine the correct position of min and max by comparing these elements with the other array element. To determine the correct position of min, we know the initial position of is already sorted, so we need to find the first element, which is just larger than min. Oh, it's still the same. It's still the same idea, but much more complicated. Okay, I like mine. Mine is actually not bad. Mine is not as intuitive as this one, but it's all wanting space, and it's way easier than this. It's four for loops. But this one, what the heck is this one? Left and right, min and max, st and nd. Don't know what that means. Start and end. While r is larger than 0. What is r? R is right. Do nums L. If it's larger than max, okay, so it's the left value is larger than max. If it is, we update max. If it is not, and equals L. Huh? Wait, what? A number's right if it's smaller than min, then min, so we update min. When we update min, we don't change start. But if nums r is larger than min, then start equals r. Hold on, I still don't understand. So we left, right? So we're going from both sides in, right? And every time on the left side we check if it's larger than the current max. If it's not, then my end is set to the left. Okay. I kind of see what it means. It means that this is a continuous increasing, right? If it's continuous increasing, which means if my left is, it's on the left side, so left side should not be bigger than the max. But the max is set to minus number, so at the beginning, the left will be smaller than max. So we set the end to the left, and then we set the beginning to the right. And then we'll go inside. Now we're going to check again. Hold. Num L is larger than equal to max. No, its first call is larger than equal to max. So update starting. We update the max value. So we know the current max, and then we know the current mean, and then it goes in, and then as we go in, if it's larger than max, and that's good, right? That means we're still in the increasing, and if it's smaller than min, and then we still in a decreasing. So it's all good as we go in. When it breaks, which means num_L is smaller than max, so we go down. Now we're going to say nd equals L. nd is end. So end is going to L. So end goes to this position, ending. And the start, if it's still decreasing, if it's increase, then the start gonna be right. It's like the increase position. Okay. And then keep going, and start and end would it change? If it's the local max, then we don't change. Local max, it is finding the max value as we go along, right? If it's something bigger, then we go to the max. We only update the nd end when as we go along. So as we go along, we suppose every value should be larger than max. So the max is the max value until L, like until L minus 1, the max value. So if my current value is bigger than that max, then we're good, and we update the max. If I'm smaller, then that value is problematic. And then we just keep going to the right. Keep going to the right and then record which one is problematic. Because we expect everybody should be going on increasing. So every time we have a decrease, we record the value. We record the index of that. And we keep recording, right? We keep recording until the rightmost, because we go all the way to the right. So we record until the rightmost. So the rightmost value that is smaller to the current max, the nearest max. And we also record the leftmost value that is currently bigger than the current mean. So these will be the leftmost and the rightmost offender. And then we do, ooh, this is brilliant. Same work as 2 loops. It is 2 loops. It is, but it's easier. It's easier. So this is the same as comparing this, right? And but I just keep noticing. No, it's not the same. It's not the same, because as we're doing this, we're just doing consecutive comparison. This is not doing consecutive comparison. This is as we go along. We keep finding the current max. We keep just step by step to find the max. And whenever the current value is not larger than the max, then that value is problematic. But we still keep the max, right? We still keep the max. And whenever it's not, then because all we need to know is the rightmost problematic index. And that index will lead to nums that index, that value, is smaller than the current max. Right? We just need to find the rightmost value that happens to be smaller than the current max. Oh, is that this solution? Not really. Not really, because we just want to find the rightmost value that is smaller to the max value on its left side. And then that rightmost value is the boundary. Yes. So I'm actually going to implement this because I'm going to write a little bit more. In the official solution, this one is achieved via a stack. It's the same concept, but my solution has O1 space. Alright, I'm going to try this one. I think this one is actually pretty good, but instead of writing 2 loops in one, I'm going to just do 2 loops. So this solution came from a discussion, a comment. So we're going to do the comment. Oh, I cannot. Alright. The intuition is that as we go to the right, each number should be bigger than the previous one. What we need to find is the rightmost number that is smaller than the max on its left side. Similarly, we need to find the leftmost number that is bigger than the mean on its right side. These two extremes form the boundary. Yeah, it's pretty brilliant. So what we're going to do is, for I in range len nums, right? We can catch every single one of them. So we can say current max equals just -1. No, -1. Yeah, it's gonna have to be this. Even better. Import math. Avoid any such complication. We just do math.inf. And then we say if nums I is larger or is larger than current max, then current max equals nums I. Else I want to say so we need to have a right equals none. Else right equals I. So as we keep going, we keep recording the rightmost value that is currently smaller. We can do larger than equal. Currently smaller than a current max, and that one is problematic. Yes. Again, once we're done, if right is none, turn to 0. So we're going to do the same on the left side. So let's be an annoying person to do something like this. Yeah, I always say this is annoying, but actually I like it a lot. So instead of current max, it's going to be current min. the right is going to be left. You know this. And I like to use a J. And this is going to be minus 1, minus 1, minus 1. And it's going to be smaller equal to min. Then current min equals this. And itself is J. And else, we're going to say left equals J. Once we're done, we're going to return. Be right minus left plus 1. Yep. I think this one is good. Nice. I like this one too. I like this one. Alright, I think we don't have time. Ah, no! I forgot. I think we don't have time to go through the discussion, like, carefully. Oh, we hit another 188. Oh, this is good. That's a good result. But I'm not going to record it here. Yeah, we're not going to have time to have a deep dive into, oh, he has a sort. Oh, man. Okay, I like this one. Dot strip. Wait, what? Ugh, what the heck? Oh. Oh. I see. Interesting solution indeed. Interesting solution indeed. So what it does is if it's equal, we're going to put a dot. If it's not equal, we're going to put a empty, not empty, a white space. And after it's all done, we're going to join them together. So it's going to be some white space, some dots, white space, dots, white space, dots. And then we're going to strip all the white space on the ends. And then the remaining string containing dots and white space in between, the total length will become the result. Good. Very, very good. Very smart. Very smart. I mean, not him, but it's pretty good. I think this is the same as this one. Yeah, same as this one. I like to write it this way. I think it's more explicit. Anyway, these are the same. Yeah. Okay, that's it. We did well. We very fast. I think maybe like what 15 minutes. We got it done via the sorting, and it took us a while to figure out the ON solution, but should be good. All right, I will end it right here. It's 11 o'clock, and I go to bed. I will see you guys tomorrow for tomorrow's challenge. Adios.